Hello everyone and welcome back to another minute concept, this time an in-depth concept about physics, particularly energy, work, and power. Now, in the title it's energy, work, and power, however we just need to retain the concept of energy here, and we're mainly going to focus on problem solving involving work and power. So if you're interested in understanding, for example, total mechanical energy and how it's conserved, as well as the formulas for kinetic energy and potential energy, I'm going to be making another video regarding that separately. So this is the in-depth video again on problem solving involving work and power. So now let's get into it. Starting from the beginning, let's describe energy, work, and power once again. So energy is the capacity of an object to do work. So work again is the amount of energy that is transformed. So you can't transform any energy if there is nothing. If there is no energy at all, then there's no work that can be done because there's nothing to be transformed. So those two go hand in hand. And it's important to note that energy is always transformed because it's always conserved. And now, when we're talking about how fast it's being transformed, how fast it's being transformed and how fast work is happening, that is when we get to the topic of power. And power is essentially just the rate of work. So it's the rate, it's how fast work is happening, and so it's also how fast energy is transformed. So as you can see here on the screen, I put a couple of cases here. However, this is going to be regarding work. So let's put a label here. Work. So work is the amount of energy that is transformed. However, work is also described as FD cosine theta. This is mathematically or algebraically speaking. This is the formula for work. Now, what does this mean? Before we get into the cases, let's see how this formula can be broken down. So, work is the product of both the force applied and its displacement. Or we can make it this delta x, for example. And we want to see the product of these two going in the same direction. So we want them to be parallel. These two have to be parallel, and we actually have a vector process or a vector formula to get the parallel components or the components of two vectors going in the same direction. And this is actually the dot product. So the dot product is described by this formula. So the magnitude of vector A times the magnitude of vector B times cosine theta, the angle that connects the both of them. So from this, we can actually see that we can transform the original equation into this way. Now we have the magnitudes of those two vectors, and we're just going to see if they're going in the same direction. And we're going to use cosine theta. And that's basically how we got this formula here. So now we can say that work is the dot product of force and displacement. And we will get to that later. So let's put this down here at the top. Oh, on top here, I mean rather. Oops. Actually, no. Let's just keep this down here. So there are multiple cases of work. Actually, there are only three, but there are cases where work can be parallel. Work can be positive, work can be negative, and there can be no work at all. When we say parallel, it can be going two different ways. So for example, these lines are parallel, just pretend, and these lines are also parallel. And what's the difference? One of them is opposing while the other one is going to the same direction as the other arrow. And the same logic applies for work. When we have a force, let's say this is a box, and we apply a force to the box. Here, let's okay. Here, we apply a force here. This is our force applied, and the box moves, let's say 5 meters to the right. We can see that the force applied and the displacement of the box are going the same direction. If they are going the same direction, that means work done is positive. And positive work is associated with not just horizontal movement, but it can also be upward movement. So for example, let's say I'm going to be lifting a box. So if we're going to lift a box, our force applied would be going up. And the displacement of the box would also be going up. So let's say this is going up 5 meters. We can see that both of them are going in the same direction. So there is going to be work applied, and it will be a positive work. Now, how about the case 2? Case 2 occurs when the force applied is opposite to the displacement. So it cannot be the displacement is well, it's also true. However, the more what's the word? The more appropriate way to describe case 2 would be that the force is going the opposite way, because the force is what's being added. So let's try visualizing, for example, let's say a car braking. We'll describe the car in a free body diagram. So when a car brakes, it wants to go slower. So the force applied is going to be backwards, right? And it's decelerating, so it's really a stopping motion. It's a stopping motion. If the car were going to the right here, it would be decelerating towards the left. Now, its displacement is still going to be to the right. And let's say it still moves 5 meters to the right, it's still displacing itself in that opposite direction. Since they're still in the same plane, they're still both on the x-axis, there is still going to be work. However, this work is going to be negative. And we can see that this is the relation now of force and displacement. As long as both of them are on the same plane, there will be work. However, if they're in different directions, that will dictate the sign of work. So now let's write that down here. Opposite directions are equal to negative work. What's another example of this? We can actually use the lifting a box question again. So let's say we're given a question, same thing here, same box, same direction. However, this time, what is the work done by gravity? So now, okay, wait, the arrow got, oops. Let's say that we have this again, and our arrow right now is going up, because we're describing the force applied. However, we're not looking for that anymore. Let's say that the box is already up there. It was already displaced. Now we're looking for gravity while it's being lifted. The force of gravity while it's being lifted. The work done by gravity while it's going upward. So going up, it's displaced 5 meters. And on the upward motion, gravity does not just disappear, it's always there. So now it's going down. You can see that the force applied by gravity is opposite to the displacement. And that's why in this situation, work does exist, however it's negative, because they're opposing each other. And now there is also the final case where work just doesn't happen. And there are only 2 scenarios where this can happen. So in a scenario where an object is experiencing a force but does not move, that means there is no work done. That's basically multiplying the force by 0 because it's not displaced. So for example, let's take this situation here where there is a wall. And a person, represented by this arrow, is pushing against the wall with a 5 Newton force, for example. Now the wall doesn't budge, the wall doesn't move. So that means its displacement was 0 meters. 5 times 0 is 0. Therefore, there is no work done. And now there's also another situation where work cannot happen if there is a perpendicular, or the angle between the force and the displacement are perfectly perpendicular. So for example, let's say that someone is carrying a bag, represented by this square. So now someone carrying a bag would need to lift it. upward so that it doesn't fall. However, when they're walking, it's only going a horizontal distance. Now you can also see already from the shape here, there's a 90-degree angle. If you wanna break it down mathematically, the cosine of 90 and the cosine of 270 are both equal to 0. And when you plug this into our equation, everything just falls apart. Well, not really falls apart, but instead it just cancels everything out. So a perpendicular angle between the force and displacement calls for a 0 amount of work done. So now case 3 is just described as if the object doesn't move. Let's use the purple one. No displacement, or let's just use delta x here. There's no delta x or delta y, and there is a 90-degree, or not just 90-degree, or perpendicular angle is present. Perp angle. There is going to be 0 work. So I hope that's clear. Basically, again, if the object doesn't move, then we have a 0 in the equation because there's 0 displacement. If the object has a perpendicular angle, we get a cosine of the angle that results to 0, which will zero out everything else as well. So that's basically those 3 cases. And we need to exercise, of course, before moving on to the problem solving, how to identify if there's even going to be any work done at all. You can identify situations that have work and don't have work simply based on the nature of the movement. So we're going to try some problems here and we're going to identify how they work. Don't worry about this, I'll bring it back later. So let's try these 2. Well, actually there are 3, but only 2 can fit on my screen, so okay, so a waiter carries a tray full of meals across a dining room at a constant speed, and a weightlifter lifts a barbell above her head. So take into consideration this set of problems, or this set of situations. Which of them has work, and which of them does not have work? So we can see that from the first one, a waiter is carrying a tray. So we know that the tray is the object, and he's carrying it, so the force is upward. Hold on, let's change our pen. We know that the force is going upward. And he's also going across a dining room at a constant speed. So the constant speed part is actually not really that important. It's just there for the free body diagram. So we'll disregard that for a bit. So he's going across the room at a constant speed. That means he's bringing it horizontally, right? The displacement vector is going to be horizontal because he's walking around, and it's not like he's gonna fly going across the room. He's going to be walking. So the displacement vector here, we'll label it as the arrow, and this one is going to be the no, actually let's just use this as force applied. We can see that there's an angle in between them. From this free body diagram, it's actually really easy to see that there's a perpendicular angle. So since there's a perpendicular angle, which would be 90 degrees, that means that cosine 90 is 0, and our equation of f d cosine theta would just be 0. So there is no work done. No work. Okay, so now let's try the next one. A weightlifter lifts a barbell over her head. So in this situation, is there work? It doesn't specify on which part, so just in general, is there work being done? We can use the object as the barbell. So let's try using that. Now, when the lady or the weightlifter lifts the barbell, it's going up. Oops, they look too alike. Hold on, here. It's going up. And when you lift something, it's also going up. So its displacement is also going up. This is our force applied. So we can see that the displacement and the force applied are going in the same direction. So is there work? There is work. So that means it's also a positive work because they're going in the same direction and they're not perpendicular, or the object is moving as opposed to it not moving. Those are the conditions for case 3. So there is work. There is work here. and work is positive. So in this situation, this can actually be broken down into two different parts, right? So as I mentioned earlier, there's the force applied going up, and there's also the force of gravity. If we're talking about the force of gravity would give us negative work. So now let's go to the next one, the last one for this one, just identifying if there is work at all. So a teacher applies force to a wall and becomes exhausted. Is there work or is there none? So I feel like this is a giveaway. I already mentioned it earlier, so let's just describe again why it's so. Let's say that this is the wall and then this is our teacher's force. Let's use purple again. So this is our teacher's force. Let's say she applies a 1 million force or something, a 1 million Newton force, and still doesn't get to move the wall. She becomes exhausted. There is no work done because the wall doesn't move at all. The wall doesn't move, but there's a force. And force, if we want to express it mathematically, 1 million times 0 is still 0. So there is no work done. And now we can move on to some more questions about identifying work. This time, in these situations, there is work done in all of them. We just need to identify the sign. So, an eastward moving car skids to a stop across a dry pavement. And our keywords here are skids to a stop, and it's also eastward moving. When you say something's eastward moving, it's going to the right, so we can just draw our box here, and then we'll put some arrows. It's going to the right. This is our displacement, and it skids to a stop. And when we're stopping, we're braking, so it's decelerating. So this is our force applied. And we can see that they're going in opposite directions. Opposite direction means negative. So that means there is negative work being done here. Now, next question. Great America, a roller coaster car is lifted to the peak of the first hill on the shockwave. I don't know what that is, but basically it's a roller coaster, so it's being lifted. Now, is there a positive work being done? First thing to see is, where is the roller coaster going? The roller coaster is going up, so let's just say that we're not going to make it any complicated like with a slanted arrow. We're just going to say that it's going up because it's lifted. And then now it's also going to be displaced going up. So its displacement and the force applied is going up. Since they're going same direction, that means the work done is positive. So that is positive work being done here. Now this question here on the last one is a bit interesting. A catcher puts out his mitt and catches the baseball. For this one, you need to really understand the question if you haven't experienced this. But actually, even if you don't play baseball, I'm pretty sure you would get this. So for example, imagine that a ball is being thrown at you. This is your glove. If the ball is going towards you, that means the force is going here. If you want to catch the ball, you want to oppose it, or else the ball will fall out. So fixing this arrow, this is going to be, this arrow over here is the force of the ball. That's us receiving the ball. However, when we want to catch it, we need to repel, or not repel, we need to oppose the force of the ball, or else it will just pass. No, it will break through our hand, right? It will break through our mitt, and we can't catch it properly. So we apply a force going to the right, and these forces are canceling each other, right, in that situation. However, where does the baseball go still? So we put out our hand with an applied force going to wherever the ball is coming from. So we're opposing the direction of the ball, but the ball is still going towards the left, right? And since they're going in opposite directions, opposite again is equal to negative. So that means there is negative work done. So I hope that's clear. Just to recount, the moving car is going an opposite way from where the force is being applied because we're braking, and braking means going opposite from the direction that we're going to. And for the roller coaster, it is going up, and the displacement is also going up because we're going towards the peak. So that means there's positive work because we're going in the same direction as our the force is going in the same direction as our displacement. And then lastly, for the last one, we decided that it was, actually no, we found out that it was negative work simply because the force that we apply to catch the ball is opposite from where the ball is still going. So now we are going to go to the problem solving portion of this topic. So we're going to recount this formula here. Okay, and I'll just shrink this. Okay, so now let's try to analyze these problems, not just based on the given, but let's also see if we can make free body diagrams out of them. Because once you're able to make the free body diagrams, you're also going to be able to break down the problems into their respective parts. You can also analyze for different givens. So a 10 Newton force is applied to push a block across a frictionless surface for a displacement of 5.0 meters to the right. Now, in this situation, we want to find the work done, the net work. So for all of these, we're actually going to be looking for the net work. So let's make the free body diagram first. So let's use our blue pen. We have the box and it's being pushed to the right. Okay, it's being pushed over there. And it's a 10 Newton force. There's also displacement 5 meters to the right. 5 meters. And we want to get the work done. So there's no friction, so there's no opposing force here. The normal force exists still because it's on a surface. Actually, let's change the color of the arrows, sorry, just so that it's distinct. Let's use yellow. So again, we're just gonna write it here. There is the 10 Newton force, the 5.0 meters. There is going to be the normal force here, which is just going to be the opposite of the force of gravity. We're gonna get that later. And there, so now we have 3 forces to look at. We have 3 sets of work to determine if there is a net work done. So let's try breaking down first our applied force. So our applied force here is 10 newtons. So let's use this one. Or actually, let's just use this one. So we're going to get the work done by the applied force. Work applied. So our applied force is 10 newtons. Our displacement is 5.0 meters. And our cosine is 0 because they're going in the same direction. It's a flat surface. Cosine 0 is equal to 1. So that's the maximized version of our work. This is the most amount of work that's possible. So we can simplify this to 50 meters. 50 point meters. Actually, no point because of significant figures. My apologies. But there. So we have our work applied. Let's move these down. Our work applied for this is 50 joules. Newton meter slash joules. So we're just gonna put here joules. Oh, also the unit for work in problem solving is joules. However, that you can also be writing this as or Newton meter. Newton meter is the conventional way of writing it. However, joules is the established other term for it, which is more used. So now let's try and get the work done by the normal force. So let's go on to the normal force now. Work done by the normal force. So the normal force is going to be at a 90-degree angle to our displacement, as you can see here. And it's also going to be experiencing the force of gravity. And then there is the 5.0 meter displacement. We don't even need to solve for the force of gravity anymore. This is okay, let's just put the negative there. The negative force of gravity is the value of the normal force. So since there's a 90-degree angle, like I said earlier, there's going to be 0 work. There are 0 joules of work. And same thing with the force of gravity. So work done by gravity, there is 0 joules. So our applied or our net work is going to be based on the applied work, which is 50 joules. Oh, it got left behind. Okay. That gives us 50 joules of work in this scenario. So there, that's how we solve for this one. We have to get the net work of every force. Of course, in an exam, you're going to have to determine first what it's asking for. Sometimes it's not asking for net work, but instead it's asking for specific works. So there. Next, a 10 Newton force. 10 Newton forces is applied to push a block across a frictional surface at constant speed for a displacement of 5.0 meters to the right. So pretty much the same thing, except now we're going to be solving for friction as well. And friction cancels out our applied force. Oops. Okay, hold on. Let's move this down. Alright, there. Actually, we can just copy this entire solution and we only have to solve for friction now. So friction here is just going to be the same as the applied force, except it's negative. We know that it's negative because it's balanced. Okay, take a look at this. We're going to write the arrow here as friction. Now it says it's at a constant speed. When it's a constant speed, it's not accelerating. When is an object not accelerating? It's when the net forces are equal to 0. So this force over here, the applied force, must be equal. Applied force must be equal to the frictional force, whereas the frictional force is negative, of course, to cancel each other out. So we're just gonna copy our solution here, and we're gonna change the sign to a negative sign there. And seeing as 50 plus minus 50 is equal to 0, that means there is no work done. No net work. Now, next question, last for this one, before we move on to power. A 2 kilogram object is pulled upward at a constant speed by a 20 Newton force for a vertical displacement of 5.0 meters. Okay, so this one's kind of different. We're talking about vertical displacement now. And it's important to understand where your forces and your displacement is going. So let's first start with the vertical displacement, because the displacement is really what is driving the entire problem. It's the basis for whether or not our work is negative, so let's start with there. 5.0 meters going up. And the object is experiencing two forces. There's going to be the upward force, which is, it could be tension, but it okay, well, let's just say that it's tension, even though it's not explicitly stated there. There's the tensional force, and then there's also going to be gravity. So Fg. Now there is going to be a 20 Newton force going up, and the force of gravity is just essentially its weight, and we'll use gravity equals 10 meters per second squared here. So to get the force of gravity, we're just going to do 2 times 10 meters per second squared, and we'll get 20 newtons as well, this time going down because they are going downward. The gravity is always going downward. So now our problem solving for this is pretty much just the same thing. However, I just want to elaborate on the axis that we're going to be using for reference here. Now, our axis normally would be this as the x and y. This is x, and this is y, right? Okay, hold on. Let me change this there. This is y. That's an example. This is y, and this is x. Now, it's different for this type of question. Why? Because there is a displacement going upward. So we essentially flip our axes, and we're going to make it like this. This is our new x, and this is our y. And why is that? This is because in order to get the cosine, we're essentially flipping the entire thing like this. And visualizing it this way, it will allow us to get the right angle, right? And it's also because if we're using the x-axis here like this, then there's a 90-degree angle. Even though the displacement is not going there, doing the cosine value of 90, because it's going upward, it's going to give us 0. So doing it like this, the other way, where this is x and this is y, this will allow us to use cosine 0. So now let's try that. So the work by the tension would be 20 newtons times 5.0 meters times cosine 0, because this is now going to be the 0 point. This is 0, 90, 180, and 270 right here. So this will give us, this is equal to 1, so 20 times 5, that's 100 joules. And next, for gravity, we're just gonna copy this equation, same thing, because they're the same quantity. Change this into g. Hold on. Make this g, and then we're going to get a negative 100 joules because the work done is negative. It's opposite to the displacement. So we can add these two together to get a net work of 0. So work net is going to be equal to 100 joules plus the negative 100. And this is equal to 0 joules, no work done. And also, the forces cancel out here, the object is not accelerating. So there. Now let's go to the power questions. This is going to be really quick. So for power, it's described by a very simple formula. It only gets complicated once work is not given to you. However, most of the time, work is given. Of course, if you aren't given work, we've already just figured out how to solve for it. So let's go. Power is described as work over time, wherein time is in seconds. So in seconds. So for example, in this question here, 4,000 joules of work in 8 seconds, what is its power output? We just have to plug and play our formula. So our power here is equal to 4,000 joules of work over 8 seconds. And just using division, you can get 500 watts. Okay, so it's watts over, it's watts, not joules per second, though that's also acceptable. It can also be joules per second. However, most tests will show you watts. And if you're asked, of course, what units does power come in, you can put watts, joules per second, or in special cases, horsepower. Horsepower has a separate conversion for from watts and joules per second. Actually, horsepower is what's used for cars. So most of the time, horsepower will be involved in questions regarding engines and stuff like that. So horsepower is 1 horsepower is approximately equivalent to 746 watts. So that's just for you guys out there who might encounter questions like this. Alright, and now let's do the final question. This one requires a bit of algebra. So we have power is equal to watts work over time. Now we're given power, so that's 600. Yeah, oh, oops, there. We're given power, which is 600, and we don't have work, so we're just going to put work. We're given time, which is 30 minutes. Now, like I said earlier, it has to be converted into seconds. So converting seconds, minutes, the 30 minutes into seconds, we do 30 times 60, we get 600 is equal to the amount of work over 1,800 seconds. And to isolate work, we're just going to have to multiply 1,800 to both sides. So 1,800 times 600 here, is equal to 1,080,000 joules. So 1,080,000 joules of work. And that is actually normally how much work most of our appliances do. To those who have computers at home like I do, you might see wattage ratings on your computer, your power supply, it might say 750 watts, etc, etc. This is actually how much energy is being transformed in your power supply. And then you can also see that in your cars. So there's actually a huge application for work and power in our daily lives. So I hope everyone learned something from this today. This is just the basic problem solving. So for more complex questions like ramps, I guess just use the standard knowledge, right? For this, basically just get the forces going in the same direction. If you need to break down the force into its separate components, then go ahead, that's what you need to do. Because if you're only going to use one component of the force, then it might be wrong. Basically, the entire concept of work is that they have to be going in the same direction. If they're going the opposite direction or on the opposite plane, then no work is happening. So you can't have any objects moving at a 90-degree angle to where the force is happening, as seen in case 3. You can also move in a certain direction but apply a force in the opposite direction, just that negative work will happen. And if you're applying force in the same direction as its displacement, then it's going to be positive work. It's all about the direction. It's all about the plane where the work is happening. And of course, there needs to be movement. It needs to be displaced. So there. I hope you guys learned something from this in-depth concept. I'll cover the topics of energy and conservation of energy in the next in-depth concept, so make sure not to miss that. And I'm also going to try to make a video regarding the ramp example I just mentioned earlier. So don't miss that, because those are important topics. And yeah, so I hope everyone learned something, and take care, good luck in anything that you guys have going on, and goodbye.